created by MindSticks Foundation Trust. Hello students, and a very warm welcome to today's class. Today, we're going to understand exactly how arranging elements by their atomic number creates a literally perfect chemical blueprint for the entire universe. It's like a giant puzzle coming together. So, let's dive right in, shall we?
Here is our quick syllabus for today's explainer. We'll be covering 5 main topics. First, the structure of the periodic table. Second, groups. Third, periods. Fourth, electron capacity. And finally, periodic trends.
Okay, starting with Section 1, the structure of the modern periodic table. Let's look at the macro layout.
Now, as you can see, the modern periodic table organizes all 118 known elements strictly by their increasing atomic number. This is absolutely crucial. By making the atomic number the fundamental property, this modern table completely removed the confusions of Mendeleev's older mass-based table. It's a much more scientifically accurate system.
Let's break down its physical structure carefully. If you actually count them, the table contains 7 horizontal rows, which we call periods, and 18 vertical columns, known as groups. Furthermore, the whole shebang is systematically divided into 4 distinct blocks, the S, P, D, and F blocks. Please make a quick note of these divisions in your books.
Now, what's really fascinating here is the zigzag line found in the P block. We already know the D block contains what we call transition elements, right? But that zigzag line is a brilliant visual guide. It perfectly separates the metals, which all sit nicely on the left side, from the non-metals on the right side. And the elements lying right along the border of the zigzag line, well, they possess mixed properties, and we call them metalloids.
Moving on to Section 2, groups and their electronic configuration. Let's understand the behavior of these vertical columns in a bit more detail.
I want you to put your thinking caps on for a moment. If we look at the elements from top to bottom in any single group, what similarity do you find in their electronic configuration? Any guesses?
Let's trace group 1, the family of alkali metals, from top to bottom to find our answer. Start with hydrogen. It has just 1 valence electron. Next, lithium has a configuration of 2-1. Then sodium is 2-8-1. And potassium is 2-8-8-1. See the pattern? This brilliantly illustrates that while the number of inner shells keeps increasing as we go down, the outermost valence electron count remains exactly 1 for the entire group. How cool is that?
Before we jump to the next topic, here is a really fascinating do-you-know detail from your text. Uranium has an atomic number of 92. Did you know that all the elements beyond uranium, meaning atomic numbers 93 to 118, are entirely man-made in laboratories? Because their nuclei are so massive, they're highly radioactive, very unstable, and literally have an extremely short life.
All right, Section 3, periods and electronic configuration. Having studied the vertical groups, let's shift our focus to the horizontal rows. Take a close look at the atomic structures of potassium and argon here. Notice how the electron shells are filled when we move across a period, from left to right. You'll observe that the total number of shells actually remains exactly the same. The newly added electrons are simply filling up that existing outermost shell. So, the crucial takeaway here is grasping this fundamental difference. When you go down a group, a completely new electron shell is added, but the number of valence electrons stays the same. Conversely, when you go across a period from left to right, the number of valence electrons increases by 1 each time, but the shell number stays exactly the same. Make sure you remember this distinction.
Section 4, electron capacity of shells. Let's uncover the strict mathematical rule that dictates exactly how many electrons each of these shells can actually hold.
The fundamental formula you absolutely need to remember for your exams is 2n squared. In this simple, elegant formula, the letter n represents the shell number. Let's apply this logically, shall we? Read through this table with me, step by step. For the first shell, the K shell, n is 1. So 2 times 1 squared gives us a capacity of 2 electrons. For the L shell, n is 2. 2 times 2 squared gives us 8. For the M shell, n is 3, giving us 18. And for the N shell, n is 4, which gives a maximum capacity of 32 electrons. It's just a beautiful mathematical progression. And now, we reach Section 5, Periodic Trends in Valency. In this final chapter of today's explainer, let's observe the natural gradation in chemical properties. First, let's quickly recall the definition. As you've learned in the previous standard,
Valency dictates the chemical reactivity of an element, and most importantly, it's determined purely by the number of valence electrons present in the outermost shell of its atoms.
So, let's summarize the periodic trend for valency based on everything we've covered today. When we move from left to right across a period, the valency varies systematically, simply because the number of valence electrons is increasing. However, when we move from top to bottom down a group, the valency remains absolutely identical, because those outermost electrons are the exact same number.
To conclude today's class, I want to leave you with a challenging thought. Knowing that the atomic number dictates everything we just learned, from shells to valency, how did the modern periodic table finally resolve the ambiguous placement of elements like cobalt and nickel that plagued Mendeleev's mass-based table? Think about how relying on this precise atomic blueprint fixes those historical errors. Keep that in mind, as we'll apply this understanding to chemical reactions in our future classes. Thank you for your excellent focus today.